In the late 19th century, James Clerk Maxwell compiled these four really important equations, and they revolutionized physics. So I would like to talk about how through these four equations we can deduce that electricity and magnetism are related and what that has implied for the human race. So I want to briefly talk about these first two. This one essentially tells you that if you have a plus charge and a plus charge, they repel, and unlike charges attract. That's what essentially this says in a mathematical form. This one says that if you have a magnet, it will always have a north and a south pole. So if I took this, if I were to cut it straight through the middle, you'd think that I would have just a south pole and a north pole, but no. Always nature creates a north and a south pole together. As you can see here, I can have a plus charge by itself, so it's a monopole. This is a dipole. Magnetic monopoles can't exist. That's what these two are saying. Now, these two out of the way, I would like to concentrate on these two equations because these are the real fundamental ones. These are the real important ones here. Now this one's named after Faraday, who's a really important scientist, British scientist, and this one's named after Ampere. So this one tells you how an electric and a magnetic field are both related. If I were to take an electric field and if I were to vary it, if I were to change it, that produces a responding magnetic field. And then likewise, if I have a magnetic field that changes, I can produce an electric field. So what this means is that, very famously, this is Faraday's experiment, if you give me a coil of wire, a conducting wire, right? And if I stick a bar magnet in there, amazingly, if I move this about, like that, I create electricity in this wire. I create a current. And then that current also creates its own magnetic field as well. So these are used in transformers, for example. So if I want to send large currents down from a power station, I can lose a lot of energy on the way. But what this allows to do is that if I have a special type of current, which is called an alternating current, I can send it through what's called a transformer station, where it can essentially change the voltage and the current in an according way. So if I send a current down, which is like has a really high voltage across it but a low current, I lose a lot less energy. So it's used a lot in transformers, and these two underpin how they work. Fun fact: if you've ever been in a car by a traffic light and the road is fairly empty, you notice that as you drive to it, if it's on a red light, if you drive near it, the light turns green. You can apply this to here. So if I'm in a car, this car is made out of metal, which obviously conducts, right? So as this goes through here, you can have a current that's set up through here, wires that are set up through here, and that, because of this property that we discussed earlier, it interferes with the magnetic field, and then that induces its own current, and then that current allows the traffic light to tell you whether you're there or not. As these cars go by, these cars are made up of huge chunks of metal, and there's a huge coil that runs underneath this ground. And as you can see, as the cars pass by, it interferes with the magnetic field, changes the magnetic field around the coil, and that produces electric current. And that's how the traffic lights know. And you might notice that if you ride a motorcycle, very annoyingly, the traffic light may not detect that you're there, and it might be on a red light even though you should rightfully have way. The problem here is that the motorcycle doesn't have enough metal, essentially. So this effect isn't strong enough. So if you're on the motorcycle and you move back and forth a little bit, you can actually amplify that effect, and then that'll allow you to have a green light and go. So we talked about how these two are used in applications, and it turns out that these two equations right here, they can offer something much more fundamental. So these four equations, if you play around with this mathematically and apply some, mathematical rules, it turns out that you can get something of the form of what's called a wave equation. So, if I take this equation, and this equation says that if I have an electric charge in space, it produces its own field. If I set this equal to 0, what I'm basically saying is that I'm in a vacuum, there are no charges nearby me. And then if I take all these four equations and I munch on it a little bit, mathematically, then I get something of the form of what's called a wave equation that describes a wave. So after doing all this, you get something that looks like this. This says that you can have an oscillating electric and magnetic field that travel at a constant speed. This actually turns out to describe light. So from these four equations, you get the conclusion that light is a wave, and it's an electromagnetic wave.